Welcome back to Bite-Sized Breakthroughs. Today, we delve into the fascinating world of transformers, specifically exploring the mysterious mechanisms behind their in-context learning abilities. Joining us is Dr. Paige Turner, who's been leading this groundbreaking research. Paige, welcome to the show.
Thank you, Alex. It's great to be here.
And of course, we're also joined by Prof. Wed Spectrum, a leading expert on meta-learning and the broader implications of this research. Professor Spectrum, thanks for joining us.
My pleasure, Alex. I'm eager to hear what Paige has uncovered.
So Paige, let's start with the basics. For our listeners who might not be familiar, can you explain what transformers are and what's so special about their in-context learning capabilities?
Sure. Transformers are a type of neural network architecture that's revolutionized the field of machine learning. They're particularly good at processing sequential data, like text, code, or even images, when transformed into a sequential representation. What makes them unique is their ability to learn from data provided within the input sequence itself, a process called in-context learning. Imagine you give a transformer a sentence like, "The cat sat on the blank." Without being explicitly trained on this specific phrase, it can use the context provided by the surrounding words to infer that the missing word should likely be something like mat or chair. This impressive ability opens up possibilities for few-shot learning and adapting to new tasks quickly.
That's fascinating. But how does this in-context learning actually work? Is it some magical black box, or is there an underlying mechanism?
That's what our research aims to unravel. We hypothesize that in-context learning in transformers is fundamentally driven by gradient descent, a common optimization algorithm used to train neural networks. Essentially, we believe that transformers are learning to learn by gradient descent through their context. It's like they're implicitly building an internal optimization process that adapts based on the data they see.
That's a bold claim, Paige. Can you elaborate on how you're connecting in-context learning with gradient descent?
Right. Here's the core of our work. We've developed a simple weight construction for a linear self-attention layer, a key component of transformers. This construction demonstrates that a single self-attention layer can be made to perform an update equivalent to a single step of gradient descent on a regression loss. Imagine you have a set of training data points, each with an input and a target value. Our weight construction ensures that the self-attention layer modifies these data points in a way that's analogous to how gradient descent would adjust the weights of a linear model to minimize the error between the predicted and actual target values.
So, the self-attention layer is basically mimicking the behavior of gradient descent on the data itself.
Exactly. And this isn't just a theoretical construct. We've tested it empirically. We trained transformers on simple linear regression tasks and found that they converged to our weight construction, demonstrating that they're effectively learning a gradient descent algorithm within their forward pass. The weights they learn closely mirror the structure we designed to mimic gradient descent.
Professor Spectrum, this is where your expertise comes in. What are the broader implications of this connection between in-context learning and gradient descent?
This is indeed groundbreaking, Alex. It suggests that in-context learning isn't just a mysterious side effect of transformer architecture, but rather a deliberate, learned behavior. This opens up exciting possibilities for understanding how transformers generalize to new tasks and how we can potentially improve their learning abilities. The research also reinforces the growing understanding that meta-learning, the ability of models to learn how to learn, is crucial for building truly intelligent AI systems.
And Paige, you mentioned linear regression tasks. What about more complex scenarios? Do transformers still behave like gradient descent learners when dealing with nonlinear functions?
That's a great question. We found that by incorporating another key component of transformers, called multi-layer perceptrons, MLPs, we can enable them to handle nonlinear regression tasks. Essentially, the MLPs transform the input data into a higher dimensional representation. Then the self-attention layers, which are now operating on this richer representation, can still perform gradient descent-like updates, effectively solving nonlinear problems by learning linear models on these deep representations.
So, the MLPs are like feature extractors, creating a space where the self-attention can then apply its gradient descent-like learning.
That's a good way to put it. This is where we start to see a parallel with another meta-learning framework called model-agnostic meta-learning, and MAML. MAML also focuses on learning a good initialization for a model that facilitates fast adaptation to new tasks. Our findings suggest that in-context learning in transformers might be operating on a similar principle, with the MLPs creating a rich representation and the self-attention layers performing the task-specific adaptation via gradient descent.
This is getting really interesting, but how does this relate to the concept of MESA optimization, a term often used when discussing the emergence of learning algorithms within learned models?
That's a great point. We're essentially observing MESA optimization in action. The transformer, through its training on a vast amount of data, has discovered an efficient optimization algorithm, gradient descent, and incorporated it into its forward pass. It's as if the model is meta-learning, a learning algorithm.
Professor Spectrum, how does this align with your understanding of meta-learning and its role in building more intelligent AI systems?
This finding is deeply significant, Alex. It reinforces the idea that meta-learning is essential for AI systems to truly learn and adapt to new situations. By enabling models to learn not just what to do, but how to learn, we can create systems that are more flexible, efficient, and robust. This research, in its elegant simplicity, sheds crucial light on how meta-learning might be occurring within these powerful transformer architectures.
Paige, this is amazing, but are there any limitations to your research? Where do we go from here?
You're right, there are limitations. We've mainly focused on small transformers and simple regression tasks. We need to investigate how these mechanisms play out in larger, more complex models used for tasks like language translation or image generation. Additionally, we've assumed a specific token construction that might not directly apply to all in-context learning scenarios. We need to explore other ways that transformers might be constructing the necessary data representation for gradient descent to operate.
Professor Spectrum, what do you see as the main challenges and potential future directions for this research?
It's crucial to explore the interplay between these mechanisms and the architectural choices we make for transformers. For example, while our research shows that linear self-attention aligns well with gradient descent, commonly used softmax self-attention and layer norm might introduce complexities that require further investigation. We also need to consider the role of other mechanisms, like induction heads, which could be working in conjunction with gradient descent to enable in-context learning. Ultimately, we need to strive for a comprehensive understanding of how these different mechanisms work together to create the powerful learning abilities we see in transformers.
And what are the potential applications of these findings, Paige?
The potential is huge, Alex. By understanding the inner workings of in-context learning, we can design more efficient and adaptable learning systems. This could revolutionize areas like few-shot learning, personalized education, and even the development of more robust and intelligent AI assistants. For example, imagine a language model that can quickly adapt to a new domain by learning from a small set of domain-specific documents. Or consider a personalized learning system that can tailor its teaching methods to each student's individual needs and progress. The possibilities are endless.
It seems like this research is opening up a whole new world of possibilities in AI. Paige, Professor Spectrum, thank you both for sharing your insights on this fascinating topic. It's clear that understanding in-context learning in transformers is a crucial step towards building truly intelligent and adaptable AI systems.
Thank you for having us, Alex. It's been a pleasure.
My pleasure, Paige. And to our listeners, remember, there's always more to discover in the world of AI. Stay curious, and we'll be back with another bite-sized breakthrough soon.